We're going to kick off chapter 13 here by talking about section 13.1, functions of two or more variables. You can see here our first two definitions are just defining a function of two or three variables. All this does is it takes a coordinate point, whether it be xy or xyz, and assigns a unique real number, which is denoted in function notation f of xy or f of xyz, depending on if you're in two or three dimensions. So let's roll right into an example here. We want to evaluate the function. So in problem number 2, we have a function f of xy equals x plus the cube root of xy, and we want to evaluate it at various different points. In this case, rather than a particular point, we're plugging in expressions in each coordinate. So what this means is wherever you see an x in f of x, we're going to plug in t. And wherever you see a y in f, we're going to plug in a t squared. All right, so we begin with t plus the cube root of t times the y coordinate is t squared. So this is t plus the cube root of t cubed, which is of course t plus t, or 2t. All right, so this is our new function now in terms of a single variable. When we look at b, it's the exact same function except for instead of t's, we're now plugging in x's, but they're the same exact expressions. So I'm going to skip all of the extra work and just say that this is 2x. And I'll just note this follows from part A. All right, let's take a look at C, which is slightly different. Wherever I see an x, I'm going to plug in 2y squared. And again, underneath the cube root. And then wherever I see a y, I'm going to plug in 4y. All right, so what we have here is 2y squared plus the cube root of 8y cubed. Cube root of 8y cubed is 2y. So our final answer is 2y squared plus 2y. All right, we have one more example of working with a function of two variables. Here they give us the function g in terms of x and y, and then we have two component functions, x of t and y of t. So we're looking for g of x of t and y of t. If you want, you could plug those in here within the notation. So this will be g of natural log of t squared plus 1, comma, square root of t, right? And so let's go ahead and plug it in. The y becomes the square root of t. I have my exponential function, and then minus 3 times my x component function, which is the natural log of t squared plus 1. And there's really no simplification we can do here. So that's our final answer. All right, so moving on, we say that if a function f is of two variables, then the graph of f of xy in the three-dimensional space is the graph of the equation z equals f of xy. So you'll notice what we're doing is we're introducing this third coordinate z, and then graphing it based on our knowledge of quadrics. And so these graphs are going to be surfaces in three space, just as we saw back in chapter 11. So let's take a look at number 36, sketch the graph of f. And we have our graph here. What I'm going to do is I'm going to replace f of xy with z. All right, and this is nothing new, by the way, right? If we had f of x equals x squared, we typically write that as y equals x squared, and then we graph it in the xy coordinate plane. We're doing the exact same thing here, except for now we're just doing it in 3 dimensions. All right, so we look at this and we recognize this to be a paraboloid from chapter 11. And so then let's give a quick sketch of this, right? If z equals 0, we just get a point at the origin. If z equals 1, we get the unit circle. All right, so let's go ahead and sketch this. Make sure to label your axes just so that I know the orientation here. We have a point at the origin, and then if we come up one on the z-axis, I'm going to draw in my ghost y-axis, my ghost x-axis, and I'll come out 1 and then piece together these traces. All right, and if you want to add additional trace lines in, you most certainly can. So here's our paraboloid in 3 dimensions. We have one more example here. In 40, we have f of xy equals the square root of x squared plus y squared minus 1. So the first thing we're going to do is we're going to replace that function notation with z. And there's one thing I want to note even before we start classifying what this surface is going to look like. Because z is expressed as a square root, one thing we know about square root functions is their range is only non-negative, right? So this tells me that I can only look at non-negative values of z. Now, once I square both sides, I'm going to lose that. So that's why I just wanted to make a note of it. I could square both sides and write this as z squared equals x squared plus y squared minus 1. And I recognize this to be a hyperboloid of 1 sheet. And to get an accurate sketch here, let's go ahead and test some various values here for z. If I do z equals 0, well, then I just get the unit circle. If I do z equals, say, let's do the square root of 3, then I get back out x squared plus y squared equals 4. So I can now see this hyperboloid taking shape. Remember, I only want half of the hyperboloid. I only want non-negative z values. And so on the z equals 0 plane, I want a unit circle. I'm going to make it dashed in the background there to indicate that it's behind the plane of the paper. And then go up to square root 3 units, wherever that may be. Add in your dashed or your ghost axes, as I like to call them. And this is just going to be a circle with radius 2. And then piece together your traces to form a surface. So this looks like half, and it should be kind of curved rather than a dog cone, a little bit more curved. This is like half of an hourglass figure. We lost that lower half because of that square root. Square roots only output positive numbers, or I should say non-negative. 0 is fine. All right, so we now understand how to graph these functions of 2 variables. Next, we want to introduce level curves. So we say that if the surface z equals f of xy is cut by a horizontal plane z equals k, then at all points on the intersection, we have this curve f of xy equals a constant. So this is what we were looking at with traces in the z equals k plane. The projection of this intersection onto the xy plane, and I want to emphasize here, we're projecting it downward onto z equals 0. This is called the level curve of height k, or the level curve with constant k. A set of level curves for z equals f of xy is called a contour plot or a contour map of f. So this is something that should be somewhat familiar to us. If you think back to a previous geography class, we often learn about topographic maps. So if you think about a topographic map of, let's say, a mountain range, you'll see a series of concentric curves or circles that get smaller and smaller as we get to the peak of the mountain, and they're kind of nested together. And what it does is it allows the reader to see how steep or how gradual the slope of the mountain is on a two-dimensional paper. That's exactly what these level curves are. Each individual curve is a level curve, and then the set of them all together is this contour plot or contour map. So I always like to think of that example of topographic maps when I'm working with these. All right, so in this example, we just want to indicate what the level curves are going to be in these particular cases, and then we will take a look at drawing an actual contour map. So example, select the term that best describes the level of curves of f. Choose from lines, circles, non-circular ellipses, parabolas, and hyperbolas. So let's take a look here first of all at B. Now remember, what we're doing is we're taking this f of xy and replacing it with z. So we would have z equals 2x squared plus 2y squared. All right, and so what's happening here? I see the sum of two squares, so that's either a circle or an ellipse. Which one is it, right? Because we have two different choices. We have circles and non-circular ellipses. Because the weights in front of these squared terms or the quadratic terms are equal, 2 and 2, we can conclude that this level curve is going to be a circle. All right. Or I should say circles, right? Because we can change our value for z. Similar thing here, we want to take f and represent it by z. This minus 2x is going to shift things a little bit, but what's important is I have a positive x squared term and a negative y squared term. So that leads me to hyperbolas. All right, and lastly, if we replace f with z here, I have 2y squared minus x. That's going to give me parabolas because I have a linear term and a quadratic term. All right, so we've had some practice identifying types of level curves. Now let's practice with sketching some. So in this example, I want to sketch the level curve z equals k for the specified values of k. All right, so let's zero in here on our function. This looks kind of like a reciprocal function here. However, I want to note that because I'm dividing by x, I need to ensure that x is non-zero. So keeping that in mind, if I solve for y, I get y equals zx. So these level curves are going to look like lines because both of my variables, x and y, are linear. So let's take a look at what these various lines are going to look like. So first of all, if z equals k equals 0, then we're just getting y equals 0. Now again, do not forget that we can't allow x to equal 0 in general. And so we're going to leave off the origin when we're sketching these. So what I'm going to do is I'm going to draw in red the XY coordinate plane. And then in black, I will sketch my lines here. So y equals 0 is along the x-axis here, but I'm going to put a hole here at x equals 0. And so I have this level curve, and I'll just indicate too that this is occurring at k equals 0. And so now we just want to incorporate additional level curves on this contour plot. So let's look at k equals 1. Then we're going to get y equals x. Similarly, if we had k equals -1, we would get y equals -x. So I'll sketch that one in. And then if k equals ±2, well, then y equals ±2x. So there's k equals 2, and then we'll do our -2. Pretend that goes through the origin. That was not my best artistry here. So k equals -2. All right, so we've included all of the level curves for the specified value, and what we have plotted here in red and black then is a contour map or a contour plot for those 5 values of k. Now, what happens if we bump up a dimension? So we talked about that functions of 2 variables, f of x, y, those graphs are surfaces. If we go up one more dimension, we now have, for example, w equals f of x, y, z. This is a hypersurface. It's 4-dimensional. We're not going to get into that, right? Because we don't really know how to envision those. However, if we come down one dimension, we're back into 3 dimensions. And so this last definition here says that if k is a constant, then the graph of the equation where we replace our 4th dimension with a constant k will generally be a surface in 3 space, and we're going to call those level surfaces. So previously we talked about level curves or level lines. When we go up a dimension, we have level surfaces. So let's look at some examples of level surfaces here. In 59, they give us a 3-dimensional function and then a specific k value that they want us to evaluate here at. So I'm going to replace my k with 7. 7 equals z minus x squared minus y squared plus 4. And now what I'm going to do is I would like to shift some things around so that I can identify the surface and to some degree accurately sketch it. So what I'm going to do is I'm going to solve for z. That's going to leave me with x squared plus y squared, and that's going to give me a plus 3. All right, so this looks very similar to something that we already sketched earlier, right? This is a paraboloid. I'll note here that this plus 3 is just going to shift my paraboloid up 3 units. All right, so as an example, if we wanted to find just a couple of traces, if I let z equal 3, oops, let's do equals, then what I'm going to get is 0 equals x squared plus y squared, and that's just a point at the origin. But if I let z equal 4, then I'm going to get the unit circle. So let's go ahead and sketch this paraboloid. I'll go ahead and label my axes here, and then drawing in my ghost axes, I want a unit circle. And piece it together. All right, so there's my little paraboloid. And of course, we understand that these go off to infinity, so yours might have extended a little bit further depending on how large of a z value you chose. All right, and so for these last 2 examples, we just want to describe the level surface. We're not going to focus on sketching it, but rather just describing it in words. All right, so 62, we have f of x, y, z equals 3x minus y plus 2z. So when I look over here at this right-hand side, if my left-hand side is a constant, my right-hand side is all linear terms, what do I have here? I'm working with a plane. So I'll just note that this is planes. Again, my reasoning is because all variables are linear. So that's the tip off that you're working with a plane. And how about 64? Again, if I replace my left-hand side with a constant, what type of a level surface am I looking at? Well, this should look very familiar. If we look back up here to 59, this is precisely what we had in 59. These are going to be paraboloids. And I'll just make a note, this is as in problem 59 that we just saw. This concludes section 13.1. So up next is going to be 13.2. We're going to revisit limits and continuity in higher dimensions.